Okay, so my title is Transitions and Phase Transitions. We already heard a few of the transitions that Avi has made in life. So one to which at least I'm partly responsible is, I was then a young faculty at the Hebrew University, and I think it was Avi's first paper about coloring three colorable graphs, and I was immediately taken by the beauty and the elegance of his work, and I said, we must have this guy. Came to Princeton, stayed an evening with them, and success. They came, they were for 15 years our neighbors in Neve Sha'anan. You'll see more about this. And yeah, we are essentially have become really a family. They lived in the 6th floor in Neve Sha'anan, Shmona Esrei. We're on the 5th, and you'll see more of this. But let me get even closer to Avi and speak about family. So Meir is here, Oded somehow didn't make it, contrary to popular belief. But there is rumor that there is at least one more missing child. So I made some attempts to look for this missing brother. I'm not sure. You all know that missing brother, but there is another one, and I wonder who would know. So this is not. We checked; it's not true. But how about this? Does anyone in the audience know who that person is? This is the national poet of Georgia, Shota Rostaveli, and we will come back to this. This is more serious. I'm still not sure whether or not this is correct, but. So I mentioned about really growing up like one family. So this is more or less what bath time used to look at those times. And Rotem, now an artist in Brooklyn, our eldest daughter, I spoke to her first. We really grew up like almost like a family. And she asked me, so you're your first speaker? I said, yes. Are you going to embarrass Avi? Presumably that's part of my job description, right? So she says, come on, are you able to embarrass him more than he embarrasses himself? And so, well, that's a serious obstacle. So, I'll come. So Avi likes very much lots of physical activities. So we went skiing several times, and it was very nice. And then she reminded me of us three sitting in the lift in the middle of the beautiful French Alps, the most civilized place on earth. And then Avi goes, Ima, 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 Rali ban shama, Ima, 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 at lo ashema. So if you think this is blues, you're absolutely wrong. This is actually very funny. And I'll try to make a translation. So Avi, one of Avi's hobbies is to translate poetry, and this is why I think he is maybe related to Shota Rostaveli, which means it's really part of a very, very funny skit. Avi knows all this material by heart, and you just push a button and he starts going. This goes something like, Mama, 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 my soul is on flame, Mama, 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 you are not to blame. But it's really very, very funny. Ask Avi. So that's another part of our ski activities. Here we are on the way up to Mount Rainier. These two heroes, Ehud and Avi, tried to go a little further under the guidance of Eyal, but somehow conditions were too bad, they couldn't. Here, this is a diving class that they took. That's Avi again. Here he's working with our son, Nadav, who was so thin that he had to really shake him into the wetsuit in order that he fits in. So here are horseback riding in the Canadian Rockies. You can recognize some of the figures. And so that's the new generation. These are our youngest, who are now graduate students. That's Yuval Wigderson in math. That's Nati Linial in astrophysics, so there is some future to this. This talk covers a part of a really big area of research that I and students and collaborators have been involved for a good number of years now of what we call high-dimensional combinatorics. Specifically, what I'm telling today is going to be joint work. I'm not going to be very accurate about giving credits. I apologize. With Lior Aronstam, she finished her PhD recently. Yuval Peled is currently a PhD student. Tomasz Łuczak from Poland, and Roy Meshulam was actually my first PhD student, professor in the Technion. So high-dimensional combinatorics really starts from the observation that essentially everything basic that we teach in the undergraduate discrete math class is one-dimensional. And these things have very interesting high-dimensional counterparts, and this is what we are trying to investigate. So today we will be talking about simplicial complexes, more specifically about the random model of random simplicial complexes. A simplicial complex, you'll see, is just the bigger brother of graphs. A graph is a one-dimensional simplicial complex, but there are lots. There are trees, there is tournaments in higher dimensions, there are permutations, there is lots of very basic combinatorial objects which have higher dimensional counterparts. They're really interesting, and so we're investigating this whole area. You know, it's a Wild West. It's really a wonderful area in which to go. I will be able to say just a word or two where this should, at some point, connect to theoretical computer science. This connection hasn't been made yet, but I'm perfectly sure that it will. Okay, so next slide. It doesn't work, this thing. Okay, so oh, this is terrible. So just, I'll say next, please, and then, okay. So our basis is next. Please go to the end of the slide. That's it. Okay, good. So our basis is it will work. It worked like this for many years in biology. I've been. It's okay. We'll next slide. No. Sorry. Okay, good. So we start. So you'll see. I mean, I'm still not saying anything about simplicial complexes, but I'm going to talk about. You already understand the simplicial complexes are the high-dimensional counterparts of graphs, and I'm going to speak about random simplicial complexes. And everything is done in light of random graph theory. So I'm first reminding you quickly of some of the fundamental things about random graphs. I'm sure you all saw them, but just as a quick reminder. So they come in various flavors. The original Erdős-Renyi papers from the early 60s worked with this model. You're considering graphs with a given number of vertices, given number of edges, and you're selecting uniformly from them. Usually the most convenient form to work with these things is to fix a number of vertices and have every edge independently thrown in with probability p. And there are good theorems that tell you how these two things are related to each other. And another one, which is also very useful and we'll encounter, is the evolution of random graphs, where you start with n vertices, no edges, and you start throwing in edges one by one. And you want to understand how the graph evolves. Can you please go on to the next slide? Okay, so again, why don't you go to the end of the slide and okay, good. Okay, good. So now we can ask various questions, and I will pose it in the different models that I spoke about here. Perhaps the most obvious property of graphs that you want to consider is connectivity. And the question is, what is the critical parameter for a graph to be connected? So a random graph with few edges is intuitively likely to be disconnected, with many edges, very intuitively connected, and you want to understand where the transition occurs. So, for example, what is the critical number of edges where this transition occurs? What is the critical edge probability or density where this occurs? And here you can actually ask the most refined version, hitting time. At what moment are you expecting this thing to occur? So can you move on to the next slide and also go all the way? Okay, good. So this last version was given a beautiful answer by Bolobash and Thomason about 30 years ago. And it tells you something very nice. I mean, it's a very fulfilling theorem. As you do this random process of throwing in more and more edges, initially all the vertices are isolated. And if you think about it for a few minutes, you'll realize that isolated vertices remain relatively late in the game. And what the theorem says that with almost certainty, the moment the last isolated vertex disappears, when you throw in the edge that eliminates the last isolated vertex, that's exactly when the graph for the first time becomes connected. And this is a more refined version of what Erdős and Renyi knew. I mean, from this you can easily derive the theorem that was derived 25 years earlier by Erdős and Renyi, that the critical probability for connectivity is P equals log n over n. There is one part of this which is really easy. If P is slightly below log n over n, then coming back to what I just said a minute or two ago, not only is the graph disconnected, you can easily show by straightforward computation that almost certainly there are isolated vertices, the graph is disconnected. What takes some work, but in today's standard this is considered easy, is that if you pass this, then almost surely the graph becomes connected. So I'm sure I'm telling you, many of you know this, I'm just, go to the end of the, yeah, okay, very good. So now I want to get into the subject of simplicial complexes. Simplicial complexes are a good point where combinatorics and geometry meet, and as I try to explain in these comments, I'm sure it will also be very useful for all sorts of considerations in theoretical computer science. Why? So a graph, I mean, I don't know if you ever spent time thinking of why it is that graphs occupy such a central place in essentially every application of the mathematical sciences to the real world. And there are many explanations, but perhaps a major one is there are lots of complicated systems that we'd like to understand, you know, in technology, in the natural sciences, in social situations, where you have a large complicated system, but really everything, the basic interaction that underlies the whole thing is pairwise. You know, it could be molecules, elementary particles that interact, and so on and so forth. And when you have such a situation, graph is really the perfect model for this. But of course, there are lots of situations where the underlying interaction is not pairwise. It's some, let's say in bioinformatics, there are several molecules, several proteins that together create some function. Of course, you can take this, turn it into a graph, turn this set into a click, but you're really missing information. So the obvious thing would be to say, okay, let's use with hypergraph theory. But hypergraph theory is nowhere as developed as graph theory. And what we are suggesting here, good, is you can think of, you're perfectly fine thinking about simplicial complexes as a very special kind of, or a special kind of hypergraphs. But as you'll see in a minute, one nice thing about working with this kind of hypergraphs, with simplicial complexes, is that it brings in geometric intuitions and ideas, which is very useful and very interesting. So what is a simplicial complex? This is a slide that you really must be sure you understand. It's actually, from a combinatorial perspective, it's something very simple and natural. It's just a closed down family of sets. So you start with a set of vertices, finite, and it's the simplicial complex is a collection of subsets of the vertex set, which satisfies just one condition, that if A is in the family and B is a subset of A, then B is in the family as well. That's all. And as usual, we have to create some terminology here. We call these members of the family simplices or faces, and we associate a dimension with them. So the dimension of a set is just its cardinality minus 1. Think about it for a second, it makes perfect sense. A singleton is a point which is 0-dimensional, an edge, 2 points is 1-dimensional, and so on and so forth. And there is this terminology, k-face is a k-dimensional face, and the dimension of the simplicial complex is just the highest dimension of a face in the complex. Okay, it's a very simple combinatorial object, very natural. Can you please move to the next one? And you can easily realize that really a graph is a one-dimensional simplicial complex because it has 0-dimensional faces, which we normally call vertices, 1-dimensional faces, which we normally call edges. The being closed down is given. And this is really the starting point of much of what we'll be doing in this area. In principle, everything that you know about graphs, you can ask, is there a similar phenomenon? Do things behave in the same way, differently, as you ask the same, you seek the same phenomena, or you ask the same questions in higher dimensional simplicial complexes. Okay. And in particular, what we're going to be talking about today is in the area of random simplicial complexes. Can you move on to the next one? Oops. So where is geometry coming in? You really think of them as simplices. Don't just call them simplices. They're really you really realize them as simplices. So for example, if you have a three-dimensional face or a set of cardinality 4, you think about them as a tetrahedron. Okay, can you move on to the next one? And then they're really glued together, and they create geometric objects. The next one. And the nice thing, I mean, the way that combinatorics and geometry interact here is that you can think of this, and next slide, and this, and this. They're all the same. Geometrically, there are two combinatorial descriptions of this one geometric object. So you can see quite naturally that these mathematical objects really are in a very natural way, part of combinatorics, and in a very natural way, part of geometry or topology. And this interaction really brings about lots of wonderful things. Next slide. Okay, so as I said, we want to speak about a theory of random simplicial complexes, in particular, something in light of this classical GNP theory. And to do this, we need to do two main things. One is to come up with a higher dimensional analog of GNP, which is so simple and natural, you have to somehow generate something analogous in higher dimension. And secondly, we need to create a dictionary which should tell us how, we'll see it in a second, how to translate questions or notions or ideas that are so simple and obvious in graphs to higher dimensions. Okay, so this is what I'll describe next. Okay, oops. Okay, and really the language that connects these two perspectives, or the one-dimensional to the higher dimensional, and the geometry and the combinatorics all together is really the language of linear algebra. This really makes things, this is a good language to speak. By the way, just a side comment, topology is going to lurk in the background of what we do today, but you don't need to know anything in topology. I'm not going to assume any knowledge, but if you do, then there are certain things here that you'll perhaps understand better than the person sitting next to you, but it's really not necessary. Okay, so we spoke about connectivity. We spoke about the threshold in GNP or GNM or the evolution of random graphs of becoming connected, and now we'd like to look for the analogous things in higher dimensions. So we do this we speak about this using linear algebra, and then things really fall very nicely in place. So you all know the incidence matrix of a graph. It's a matrix that rows are indexed by vertices, columns by edges, and if there is the edge ij in the graph, then there is a column corresponding to this edge. In this column, there is a +1 in the ith row, a -1 in the jth row. All other places are 0. You could ask why not the opposite. Doesn't matter. You have to fix it and go on with that. So that's the incidence matrix of a graph. That's fine. Go all the way down. Okay, so one thing that you easily realize when you think about it, let's think about now the left kernel of this matrix. Obviously, the all ones vector is in the left kernel. If you multiply on the left, you just get a +1 and -1 and get a 0. And for the same reason, if the graph is disconnected, then if you take the incidence vector of any connected component, that also satisfies the same equation. It's in the left kernel. And in fact, we really get a very nice condition stated in the language of linear algebra that the graph is connected if and only if its left kernel, the left kernel of its incidence matrix is one-dimensional. That's fine. Now we soon are going to be able to speak about this also in higher dimensions. That's how we will do so. Please go to the next one. Oops. Okay. So the analogous thing in higher dimension is what's called the boundary operator, which we denote by del. I'll explain this in a second. So connectivity means, so how should we speak about connectivity in a higher dimension? We're asking whether the left kernel of this matrix, of the boundary operator, is it trivial or not? That's the condition that we have in mind. And in the language of topology, the graph is connected if and only if its zeroth homology is trivial. But this is just words. We're not really going to use it. Next slide. Okay, so now we're really seeing something, a very general phenomenon that we encounter over and over again, that various things that are really very simple and obvious in graph theory, in dimension 1, they become richer. Even the definitions and the concepts, there is much more to think about. There is much more conceptual work to do, which is really nice and interesting. So again, think of this at the moment just as words. The analogy that we're drawing is we want to think of the analog of being connected as the vanishing of the d minus first homology, whatever that means. So I was asked not to skip things if so I'm skipping this. Let's go on to the. It's beautiful stuff, but we're a little short on time, so I will not tell this. Okay. So remember, we said that there are two things that we need to do, just to remind you where we are. We have to create a model for random simplicial complexes, and we have to create a dictionary that helps us translate concepts from graphs to the general level of high-dimensional simplicial complexes. So together with Roy Meshulam, about 10 years ago, we came up with a very simple and nice model, which is the high-dimensional analog of G and P. What do you do? So it's called X, D, and P. So N is the number of vertices, D is the dimension in which we work, and P is the same P as in G and P. So what do? You start with N vertices with a full D minus 1 dimensional skeleton. So every face of dimension D1 and below, or sets of cardinality D and below, are there. And faces of dimension D, or sets of cardinality D plus 1, you throw in independently and with probability P. And if you spend a second thinking about this, when D equals 1, this is precisely G and P. Okay, next slide. Okay, so now if you go to the full D-dimensional simplicial complex, now I want to explain, this is the analogous thing to the incidence matrix. So what is it? It's an n choose D by n choose D plus 1 matrix. It's indexed by subsets of cardinalities D and D plus 1 respectively, or dimension D minus 1 and D. And if the D plus 1 set, or the D-dimensional face, contains this D minus 1 dimensional face, then and only then will there be something non-zero. It will be plus minus 1. And it's going plus minus alternately. That's all. You fix an ordering on the vertices, and you go plus minus. And this is the boundary operator. That's the high dimensional. So again, D equals 1, that's precisely, I've described to you the incidence matrix of the complete graph. Okay, next slide. So how do we speak about, how do we put all of these things together? So let's come back and restate the Erdős-Renyi result in this perspective. So you start with the n by n choose 2 matrix of plus and minus 1 in each column. You pick a subset of the columns independently and with probability P. Now we have selected a graph. And you'd like to ask, what is the critical P for the left kernel to be trivial? The same thing we do here in higher dimension. We start from this matrix that I have just described to you. You pick columns independently with probability P. And we want to understand whether or not the left kernel is trivial. But this issue that was completely obvious in the one-dimensional case, namely it's just the one vector, or the one-dimensional space spanned by the all ones vector, that becomes a bit more subtle now. Next slide. Why? Because when you multiply two, go all the way to the end. Yeah, when you multiply two such matrices, consecutive matrices, you'll realize very easily, that's a one-line calculation, and if you took any topology class, then you must have seen this, but it's really very easy to verify that the product of two such consecutive matrices is the all zero matrix. Now we're interested in the left kernel of this, so this means that the row space of this guy is contained in this. So trivial or not means whether or not there is anything additional other than the row space of this. The row space of this is going to be there. The question is there anything additional? And remember, from this matrix, we took a subset of the columns independently and with probability of P. If P is large, then you can show that this is actually, if you take the full matrix, that this is really the left kernel. So if you take all the columns, or almost all the columns, you don't expect anything new. But as you take fewer and fewer, as P goes down to 0, then something new will emerge. There will be something additional in the left kernel, and this is exactly what we're asking. What's the critical P for there to be something additional, non-trivial, in the left kernel? Next slide. So let's think about it for a minute. Let's recall the Bolobash-Thomason answer. It turned out, quite unexpectedly, I mean, for us, it's we've got used to this, but But to begin with, it's quite surprising that really, probabilistically, the critical condition for the graph to be connected is that there are no isolated vertices. How do isolated vertices look like from the perspective of this linear algebra? An isolated vertex translates into a row that is all zeros. That's a vertex, and there are no edges there. So obviously, when you have such a thing, there is something non-trivial in the left kernel, namely, you put a 1 for in just a singleton in the coordinate corresponding to that vertex. Same thing can work here as well. So if the matrix becomes, if the P is so small, the matrix is so sparse that some row becomes completely zeros, then you know that there is something non-trivial in the left kernel. And this turns out to be the case. So can you move on to, so this is what was our theorem with Roy Meshulam, and this was, again, I'm not going to be very good in giving precise credit, so bear with me on this. That's the theorem, which is really very satisfactory. It says that the same phenomenon happens in higher dimensional as well. Namely, the critical probability for there being something non-trivial in the left kernel is precisely what happens when isn't there a row that's all zeros. Can you move on to the next slide? So exactly as we had it before, if P is below this number, then it's very easy to show that there will be a row of all zeros, and obviously then there is something non-trivial in the left kernel. And what takes work, and that's already quite substantial work, above this, there is nothing else. Okay, so that was the first theorem that really started this whole undertaking. Next slide. Okay, so I was asked to skip things. I'll skip things. Next slide. Okay, good. Good, so really, the talk starts here. So this was all background, and now I'm starting to tell you about phase transitions and so on. That's the main part of my story for today. So really, perhaps the most dramatic and very thoroughly studied and very beautiful mathematics about this was the discovery that Erdős and Renyi have made about the phase transition in GNP. Turns out that around P equals 1 over n, or if you think about this evolutionary process of adding edges, around the time that you add something like a half n edges, something very dramatic happens. And many things. This is really a moment of great changes. As you begin, think about it. It's, you know, even if you never saw this, it's quite easy to at least understand some simple things. You start with n vertices, no edges. You start throwing in edges. Initially, the edges are here and there. They don't touch each other. As you throw more and more, they start touching each other. And for a while, you'll get very simple and small connected components. Simple means they're all trees, possibly with a Poisson number of unicyclic, so 3 plus an edge. And then, at around this time, something dramatic happens. A giant component emerges, but there is more. This is for the first time, this time, the graph is no longer a forest, almost surely. And right, so with probability that's bounded away from 0 and 1, as long as you're bounded away from 1 over n, the graph is still a forest. But above this, if you're going to 1 plus epsilon over n, it's almost surely not a forest. Next slide. Okay. And the thing that really got a lot of attention, and I'll tell you, this was a major thing that we wanted to accomplish, and now we know how to do, is that they proved that a giant component emerges around P equals 1 over n. Giant means proportionate. So a constant fraction of the vertices are in one big component, and this was analyzed really to amazing depth and accuracy. And this was sitting there, and we were wondering, you know, is there an analog for this in higher dimension? So next slide. Okay, so I've told you many things now. One is around P equals 1 over n, the graph is almost surely no longer ceases to be a forest. Well, that sounds something like that we can handle in higher dimension, because a forest just means an acyclic graph, and cycles, you'll see in a second if you have known this before, is very easy to define also in higher dimension. One thing that was a major obstacle for us is conceptual. Because unlike in graphs where there is a obvious and simple notion of connected components, such things do not, there is no notion of connected component in dimension 2 and above. How are we even going to formulate, let alone prove anything? Just what are we going to ask? What are we seeking? So you'll see there was a nice conceptual thing that we found out. So next slide. Okay, so about cycles, that's very simple. The cycle space of a simplicial complex is just the right kernel of the boundary operator. So in the graphs, the right kernel of the incidence matrix is just the cycle space of the graph. So that's nice and simple. Next slide. Okay, so I recall the following theorem, which we are teaching our students in undergraduate study, or principally we should be. But if you have the following conditions are this equivalent for a graph with n vertices, n-1 edges. The graph is connected. It's cyclic. We just call it a tree, of course. It's collapsible. Collapsible usually we don't teach, but there's really no reason not to do this because it's completely elementary. So next slide. What is collapsibility? What is a collapse step, an elementary collapse step for graphs? You take a vertex of degree 1 and you throw away that vertex and the single edge that contains it. And what is an elementary collapse in higher dimension? You take a d-1 dimensional face, so think d equals 1, 0, that's a vertex, that is contained in a unique d-dimensional face, and you throw both of them away. And we say that a d-dimensional simplicial complex is decollapsible if by repeatedly performing these steps, we eliminate all the d-dimensional faces. So it's very easy to see that that's a condition for a graph to be a forest. And it's all very simple. And it can be understood, so I will, when I thought that I had perhaps too few slides, I thought I'll elaborate on this, but I have already too little time, so I will not go about this. But this can be very, very easily understood. If you have some background in topology, it's very simple. It's a homotopic equivalence. But also using very simple combinatorics, you can convince yourself that collapsibility implies acyclicity. A decollapsible complex, that's very easy to show. I mean, in 2 minutes, I would have shown you the proof of this, but it's really is acyclic. Next slide. Okay, go all the way to the end. There is one more thing here. Okay, good. So, I mean, if you never saw this, and that's one memento that you should take home with you. So what is this? That's a beautiful example which gives you a sense that high dimensions and one dimension, why don't you sit in a place that you see? That's the 6-point triangulation of the projective plane. So notice that this guy and this guy are the same vertex. There are 6 vertices here. There are 10 faces, 2-dimensional faces, 2-dimensional simplicial complex. That's a 2-dimensional face, or 2-face, 4, 5, 6. That's 3, 4, 6. And it's non-collapsible. Why? I mean, how do you start collapsing? You're looking for an edge that is contained in a unique 2-face. A 2-face is just a triple, and there is none. Every edge here is covered twice. So if this looks to you like it's covered only once, no, it's covered both here and here. Okay? So every edge is covered twice. You cannot even start collapsing. And now, I said, perhaps a bit carelessly, the right kernel and so on, that all depends on its linear algebra. There is an underlying field, or there is something, and indeed, you see the difference here. This is acyclic, let's say, over the reals or over the rationals, but it's not, it is cyclic over the field with 2 elements. So the situation you see, the plot thickens here. It's really, things are becoming richer and more complicated as you go up in dimensions. So go to the next one, please. Oops. So this means, at least I think now we have our questions formulated. We can ask, what is the threshold for decollapsibility in this model? What is the threshold for acyclicity? In particular, are they the same? Since we have the implication that a collapsible complex is acyclic, it is clear that this inequality holds. Is this a proper inequality, or is it actually an equality? Next slide. So this is really, so just, this theorem covers 5 papers. So And we should give credit to all the people whom I mentioned at the beginning. But now we have a very satisfactory answer for this, for all these questions. So for every d that's at least 2, there are 2 constants, gamma d and cd, such that in this model, the threshold for decollapsibility is gamma d over n, for acyclicity is cd over n, and these things asymptotically in d behave very, very differently. So gamma d, the threshold for collapsibility, the numerator there behaves like log d. For acyclicity, behaves something like d plus 1. So in particular, the 2 phenomena are really statistically very, very different from each other. So the implication that being collapsible implies acyclic goes away a very long way. It's far from being an equivalence. Okay, so this is, so as I say, these are 5 papers. I mean, there is fairly substantial work involved in this. I'm not going to try and get into any of the details. I'll just try to give 1 or 2, bits of ideas or intuitions what went into this. There is in the theory in graph theory, but in particular in the theory of random graphs, people have investigated the notion of the emergence of the k-core. What's a k-core of a graph? It's the largest subgraph in which all the vertices of degree k and above. How do you find this? Why is it there? Because it's very simple. You simply throw away every vertex of degree below k. Either you have eliminated the graph altogether, so there is no k-core, or something remains. That's the k-core of the graph. And there was a question that stood for about 15 years. What is the critical p for the emergence of the k-core, and how does this happen? Now, if this business of peeling off vertices of low degree reminds you of this notion of collapsibility, you're right. And actually, we are using ideas from this. There's very beautiful and substantial ideas that went into there, and we have, in fact, used some of this technology in order to solve some of our problems. Next slide. Okay. Another very important idea, which we only realized at the very end how we're doing this the whole time, and it's really very interesting and very important. There is an idea in random graph theory. When you want to understand a random graph in GNP, you sometimes work instead with what's called the Galton-Watson tree, where there is a root, and think of this as, this is a genealogical thing, a parent giving birth to children and so on and so forth, but it's a tree. And somehow, by looking at this infinite object, potentially infinite, this Galton-Watson tree, you really learn a lot. So first of all, it gives you wonderful intuitions of what you should be expecting in the finite case. And secondly, many of these arguments can actually be turned using this theory of weak local limits, or the notion of weak local limits, into proofs in random graph theory. We do this time and again, the whole time. We study, so we have something analogous to this, and we study the local structure of the simplicial complex by using that idea. Next slide. Okay. So one more small idea about the threshold for there being cyclic. So here is a very simple observation. We are looking for a right kernel. Is there a right kernel for the cycle? So if you have a matrix that has more columns than rows, then there is a linear dependency among the columns. But you could also throw away all the zeros. That remains the same. You could also do these collapsibility steps. And that's exactly, it turns out. So that's, again, an intuition, a very simple intuition that turns out to be, neither part is easy, but it's a good source for the intuition. When you do these things, when you take the incidence, when you take the boundary operator, and you do all the collapses, and you throw away all the rows that become 0, and if now at the end you have more columns than rows, then clearly there is a cycle, and it's this critical P for which this is the case. This turns out to be precisely the critical P for cyclicity. Again, everything is quite a lot of work, but I'm not getting into any of the details, so please go to the next one. Okay, one thing that I wanted to explain, I mentioned that we didn't have the terminology to even speak about connected components. How do we do this? So this is in work with Yuval Peled. In some other work, we came up with this notion of a shadow. So what is a shadow? And this turned out to be the key to formulating the problem and then eventually to solve it. So what's a shadow in a graph? Let's say you have a graph and you have an edge not in the graph. And such an edge can be either in the sun or in the shade. It's in the sun if it connects two different connected components. It's in the shade if both vertices are in the same connected component. In other words, it's in the shade if and only if when you edit, you create new cycles in the graph. The nice thing about what I just said is that this translates almost word by word also to higher dimensions. So go next one. You can make the very same definition here. You have a d-dimensional simplicial complex, and there is a d-face that is not in the complex, and it's in the shade or in the shadow if when you edit, you increase the cycle space. So there is this notion. Next slide. So it's really not hard to show it. It's actually very simple that in graph theory, around the time that the giant component emerges, many things happen at once. So the graph almost surely has a cycle that we discussed. You get a giant component of size linear in n, and the shadow becomes quadratic. So we're hoping, and eventually this turned out to be the case, that the same thing is true in higher dimension. That was key for what we did. Next slide. Oops, they shouldn't see this yet. You haven't seen nothing. Okay. So this is one thing that we actually show, that around this threshold for cyclicity, this is precisely when the shadow becomes of full cardinality, of n to the d+1. So this I'm a great fan. I think Avi is not such doesn't like it so much, but I'm a great fan of experimenting on the computer. I mean, for me, it's really crucial. Luckily, my students know how to program. Sadly, the professor doesn't, but it's okay. We come along fine. So now go to the next slide. This is really a nice story. So undergraduates in the Hebrew University in CS must have do a programming project. And in the early years, people like this would come, knock on my door. Do you have a programming project for me? I'd say, go away. I'm a mathematician. What do you want with me? And it took me a few years to understand that that's a gold mine. You know, there are clever, enthusiastic kids. You just tell them to do something, they do it. And so came this guy, very good guy. And I was starting to think about these things. And first I wanted to see, can this guy really program? So I gave him something that I knew what the answer was going to be. I let him run the evolution of random graphs. So let me explain what this is. So first of all, we are dealing here with GNP. In fact, the evolution of random graphs, n is 100. And now this shows what is the probability that in step so and so much, the edge is in the sun. Okay, so initially it's in the sun, of course. And the probability, you see, around time 50, a half n, this deviates. It's no longer, it's bounded away from 1, it's bounded away from 0. Actually, if you look at this is also very nice. You can even see the log n over n of connectivity where it's really getting to 0. So this is all, I knew exactly what I was going to expect. This was known in ages, and the graph that he brought back to me, I knew everything was fine. I mean, the guy was obviously very clever, and he knew what he was doing. Wonderful. And so now I let him do the same thing in 2 dimensions. So same thing. You start with a complete graph, and you start throwing in triples at random, and you ask, what is the probability that the new face that I've thrown in is in the sun? It's linearly independent of the previous columns. Next slide, and this is what he came with. So, I mean, this is a picture at which I looked for hours, It's trying to tell me something, and I don't understand what this is. I mean, the one obvious thing is this sharp drop, and this thing here. So eventually our theorem now, I don't know how many years, but it's at least 5 years it took us, but now we can explain everything that you see in this picture. And in particular, next slide, there is, go to there is really a big difference, which physicists usually take for granted, that in the one-dimensional case, in graphs, the limit function is continuous, but it has discontinuity in the derivative, whereas in d equals 2 and above, the phase transition is such that the limit function is discontinuous. There is still tons of things to investigate here. It's really, I mean, I'm very satisfied with this, that we now have a full story to tell about this, but there is still tons of interesting and open questions in this area. It's really a marvelous area. I'm really very happy with this whole undertaking. And with this, I'll finish. So next slide just says, Mazal Tov, Avi.